This example is similar to the one that we just did. We're trying to find the slope of a tangent line to a graph, but this time the implicit differentiation is going to be a little bit more complicated. And that's why I think they gave us another example of the same type. So let's start, and I would write small here because it's going to take up a lot of space. So let's start from the beginning. They give us the equation 3 times x squared plus y squared equals 100 x y. So there's a couple of options. Some people might use the chain rule on this and then use the product rule over here. Some people might FOIL this out. There's a bunch of different roads you could take. I think I'm just feeling the whole FOILing it out. I don't think the FOILing is going to be that bad, so that's the route I'm going to take. Maybe it's a mistake, but whatever. It's math. It's not like a life or death situation here. So I have the 3. I've got x to the 4th plus 2x squared y squared plus y to the 4th. And that equals 100xy. Just another restatement of the original problem. Now I'll distribute 3x to the 4th plus 6x squared y squared plus 3y to the 4th equals 100xy. Already I'm identifying some problem areas. This expression and this expression are going to both require the product rule. So just be aware of that. I'm going to actually set them off with brackets just as a reminder, hey, I got to do something a little bit different with these guys. So let's start the differentiation process. The first derivative is going to be 12x cubed. That was pretty simple. Plus. And now what I'm going to do is I'm going to partition off to put my answer of the product rule. I'm going to forego the whole f prime, gg prime chart, and I'm just going to do this manually or verbally. So it's going to be the first expression, which is 6x squared, times the derivative of the second, 2y dy dx, plus the second expression times the derivative of the first, which would be 12x. So this is the result of just having done this right here. Now we're on to the third term, plus 12y cubed dy dx. Now when I go to the other side of the equal sign, I'm going to have to do the product rule again. So it's going to be the first, 100x, times the derivative of the second, dy dx, plus the second times the derivative of the first. Yuck, right? Just take it nice and slow. It is what it is. You have to have some perseverance to carry this all the way to the end without giving up. So just cleaning this up a little bit, we have 12x squared y dy dx plus 12x y squared plus 12y cubed dy dx equals 100x dy dx plus 100y. So now we're going to have our dy dx party. So we have 12x squared y dy dx plus 12y cubed dy dx minus 100x dy dx equals, we have our 100y all already on the right hand side, and then I'll bring with it minus 12x cubed and minus 12xy squared. Now we're going to have we were having our dy dx party. Now I'm going to factor out the dy dx. And we're left with 12x squared y plus 12y cubed minus 100x equals 100y minus 12x cubed minus 12xy squared. And then we'll do the division. Now I'm running out of room, so I'm going to come up here. Dy dx is equal to 100y minus 12x cubed minus 12xy squared, all of this over 12x squared y plus 12y cubed minus 100x. So there's the derivative. I am observing that every one of these coefficients is divisible by 4. That might make the math a little easier when I substitute in, so maybe I should go for that. This will leave me with 25y minus 3x cubed minus 3xy squared all over 3x squared y plus 3y cubed minus 25x. Okay, my hand is really starting to hurt now. Here's my x, here's my y. I'm going to substitute those values in. So we've got 25 times 3 minus, no, that's wrong. That's a y. 25 times 1 minus 3 times 3 cubed minus 3 times 3 times 1 squared all over 3 times 3 squared times 1 plus 3 times 1 cubed minus 25 times 3. Okay, we're almost there, almost to the finish line. 25 minus 3 cubed is 27 times another 3 is 81, and minus 9. And then this is going to be 3 cubed is 27 plus 3 minus 75. Oh, I can see the finish line here. This is going to be 25 minus 90. And this is going to be 30 minus 75. So we get negative 65 over negative 45. Two negatives make a positive. Both of these are divisible by 5. 13 over 9. Now, of course, the most fun part of all this is checking the back of the book or looking up the answer somehow and seeing if you got it right. The next example has us finding a higher order derivative, the second derivative, in fact. So to do this, we're going to need to use implicit differentiation perhaps twice. Let's see what happens after the first round. So in our first round, we get 2x plus 2y dy dx equals 0. 2y dy dx is equal to negative 2x. Dy dx is equal to negative 2x over 2y. Dy dx is equal to negative x over y. So this is our first derivative, and we end up with negative x over y. So to take the derivative of the derivative, we're actually going to need to use the quotient rule. So let's come up here. I think I'm going to switch colors, and let's do this. We'll do it old school. F prime, G prime. So the top function is negative x. Its derivative is negative 1. The bottom function is y, and its derivative is dy dx. So remember, it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So the second derivative with respect to x is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. So let's clean that up a little bit. We have negative y plus x. I leave that blank intentionally for a reason. Okay, we don't want to leave an answer with dy dx if possible. So if we go back here, dy dx was defined to be negative x over y. So I'm going to make that substitution, negative x over y. And then if I clean this up, we have negative y minus x squared over y all over y squared. This is a complex fraction, which I'm going to take care of by multiplying by a useful form of 1, which I think would be best to use y over y. And doing that, we get negative y squared minus x squared all over y cubed. Now, from the top, I could take out a negative, and I'm left with x squared plus y squared all over y cubed. But if I look way back to the top, the original problem, x squared plus y squared is 25. So I'm going to come over here, and I'm going to say that the answer is negative 25 over y cubed. And I got a little lazy with notation. We just found d, the second derivative of this original problem. So here is the second derivative. So what's interesting about this is you have to be on the lookout for all these opportunities to substitute and make your answer look a little bit better. When you're finding the second derivative, you really don't want to express the answer to that in terms of the first derivative. So you want to try to substitute in if possible. And then when we got to the final answer, we were able to substitute the original. Now, you're not always going to be able to do that, but if you can, you should.